Good morning. All right, so we have graphs, qualitative, which basically means they don't have any numbers on the axes. Put any numbers in there. Let's say you guys are graph over time, x-axis. I don't see graphs that's going on when it's not a straight line from beginning to end. There's basically 2, 3, 4, 5 parts of this graph I think is going on. And is it linear for part of it? Yeah, it's actually linear for part of it.
So it's like halvesies?
That always happens, like you write
Just the first from downloading, okay? With zero got 0% download, and it downloaded for a while until the line got. What's going on there?
It stopped.
Well, before it stopped, what's going on until it stops?
It's downloading.
It's downloading how?
Slowly.
How do you know? Ooh, how do you know it's slowly?
Because it goes higher. Well, actually, it doesn't look too slow. There's no numbers, so you can figure it out.
Excellent point. There's no numbers. You can't really tell if it's slow or fast. Very smart. Here's my question: is it downloading at a constant rate of change?
No.
In that part only,
Yeah.
because it's straight. So it's downloading at a constant rate of change, and then I think somebody said it.
Stop.
It stopped. Why? Guys, we're downloading something. You guys ever see your download stop?
Yeah.
What word do they sometimes use there?
Good connection.
There's no connection.
Error.
No paused.
Error for
Buffering. I think I heard. Okay, might be buffering right there. Okay. Now let's talk about part C. This part right here. What's going on here? Of course it goes blue. I hate when the green part goes blue. Okay. Part C. Is it constant rate?
Yeah.
Is it downloading faster or slower than part A?
Slower.
Faster.
Slower.
I can't tell faster or slower. I'm hearing everything.
Slower.
How can you
Slower because
tell?
it's steeper. Steeper.
Steeper, so it's.
Faster.
seconds.
I think it's faster because more. Think about it, Matt. More is getting downloaded in a shorter time, so it's going faster when it's steeper. Okay, and then.
It's also not the same way.
And it's also not the same as part A. Right? Then it's buffering or slowing down or not lost connection something, and then a constant rate again. Okay? So that's what's going on there for that situation. But again, there's graphs where there's no numbers, and you guys gotta just talk about and make good decisions of what's happening in each area. Okay? Alright, jump to the next page. Or the one below it. You already got it. Okay. Here we go. We wrote this up. Here's a graph of Kevin walking to school. Okay? So, how many of you guys walk to school? Okay. Do you walk at the exact same pace from the time you walk out the door until you get here?
No.
Well, what about when you come to a street?
Well,
You stop and look, hopefully.
not unless.
Hopefully you're not just going through the street without looking.
I don't stop.
You might get run over. Okay.
No.
What?
Like Elf.
Like Elf? Oh, yeah.
Yellow
Like
ones
Elf.
don't stop.
All right. So, some things are going on here. Well, I'm not going to. It shows the relationship between blank and blank. Everybody figure out what are the two things, the x and the y, that we're trying to relate here in this graph.
A and up.
Look at the labels of the graph.
Distance you walked in a number of times.
Yeah. And I always do x first. I'm going to put, it shows the relationship between time and distance from home. Doesn't want to work today. Distance from home. Okay? Think about it. When you walk out your door, you are 0 feet away from home, and the time is just starting, so it's at 0 as well. What's happening in point A? And then point B, all of a sudden something else happens. Here's all the options. See if you can put A, B, C, D, E, and F in all these situations, because here's what this is what's going on at all these spots. You just got to match them up correctly.
Wait, do we write that out? Like spaces?
Put the letters in the blanks. Okay. Maybe read the options first. And then you can figure out which one is first. Which one's part A?
Slowly starts walking to school.
Ooh, why slowly?
Because it's
Because it's more of a longer time.
Well, the slope is not very much. I think A is slowly starts walking to school. Raise your hand if you think you know what part B. What happens in part B?
University.
Raise your hand. What happens in part B? Connor.
He realizes he forgot his Chromebook and runs home.
Okay. Realizes he run. Is that right?
No.
I don't know. Wait.
No.
I say sobs to help a little kid.
Hold on. I got the answers right here. Yeah, that is it. He realizes he forgot his Chromebook and he runs home. Look at that, steeper than his walking, so it's faster. What's happening at point C of the graph?
Runs at a quick pace.
He grabs his Chromebook.
Grabs his Chromebook. Okay? Here, because he's at a, look at, here, a bunch of time has gone by, but he's no farther away from his home than he started because the y-axis is your distance from home and it's back down to 0. So C is where he grabs his Chromebook. Okay? Somebody raise your hand and tell us what's going on at part D of this graph. Van Pelt.
He runs at a quick pace to school.
He runs at a quick pace to get to school. Very good. Okay, notice it's pretty steep there. Okay, we only got 2 options left. What do you think happens at point E? Minetti?
Stops to help a little kid and comes back.
He gets the
Kevin is a good kid.
the Good Samaritan Award for this guy. He stops to help us. And then at F, what happens?
Gets to school.
He gets to school and stays there for the day. Wait.
That's weird.
Why is it flat?
Because he's there.
For the day. For the day.
He stopped at school.
He's not going any farther from. You guys are not any farther from your house than you were at 8 o'clock when you got here.
Well, if I go that way.
Technically, you might be a few feet depending on where you are at the building. Okay, technically yes, but we're talking about, you guys have been in the building all day. You're not getting any farther away from your home for the most part. So this is probably something you're gonna have on the quiz. Can you do this? I think so. All right, jump to the next page.
Is this our homework?
No, this is not what you're gonna be doing for homework.
Oh, okay.
All right.
Sketch a bar graph.
All right,
showing
you're gonna
you
sketch
taking
a
bath.
graph showing you guys taking a bath. Okay? Yeah, who takes baths anymore? But there's a reason we get this. You still take baths, good. Way to go. All right. Here, we have labeled the axes for you. Over time, you're gonna take a bath. What's the amount of water in the tub?
Gallons.
50 gallons.
Well, no, we're not talking about any numbers. What would the graph look like? Okay.
Oh, it would just be going up. You'd be
Wait,
constant
so
rotation.
what happens when you walk in the bathroom and you put the plug in and you turn the water on?
It's
Right,
constant.
this instant you do that, how much water's in there?
0.
Well, how much time has passed?
0.
So, I'm going to start at the origin. Okay?
Gotta
I'm
fill
just going to
the
start at the
tub.
origin. Now, let's think about this if it's like linear or not. When you turn the water on, the hot water, the cold water on, do most faucets pour water out at a constant rate?
Yes.
Does anybody's faucet kind of like go for a little bit, then give a bunch of water, spit out water, and then stop? And
Yes.
no, I mean that means if you got bad pipes or something like that. But for the most part, would you say that the water coming out of your faucet is constant?
Yes.
Yes. So over time, the tub is going to fill up with water. So I'm going to make a nice straight line angling up. Okay, again, we're not doing any numbers. No numbers. Don't worry about the numbers. And then when the tub gets full of water that you're happy with, what do you guys do?
Take a bath.
Stop the water.
Stop the water. So how much more water is going in when you turn the water off?
0.
So what kind of line am I going to draw?
Horizontal.
But time is still moving on. Okay? You've turned the water off. No more water is going into the tub, but time is moving on. Okay? And you jump in there and you take your nice little bath.
And I have a duck with
There's no more water in it. Some last period they want to say, well, there's more water in there now because you've jumped in there.
No,
It's
it's
not
not.
water.
It's just rising.
What's that called?
Water
Displacement.
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 Actually, if
There's
anything,
no
you
more
lose
water in
water.
there. Same amount of water. It's just you're in there now, so the water level
You
rises.
could
So
lose water.
now you're done. You've scrubbed yourself. Everything's good.
Can you be with a rubber duck?
Okay. You get out of the tub. What do you do?
Drain the
Drain the water.
Drain the water. Do you think your drain drains water at a constant rate?
Yes.
Yeah, it doesn't like a little bit go, then all of a sudden it goes out. Okay, so I think this would be a great graph of when you're in your tub, taking a bath. You put water in it, you stop putting water in it, you get in and take a bath, time moves on while that's going on, and then you drain the water at a constant rate. Okay, does that make sense?
Yeah.
Sweet. All right, let's look at another one. All right, the graph at the right displays the temperature throughout the day. Okay, describe the change in temperature over time. Well, somebody made one intelligent comment about the temperature over time of the day.
The parabola.
Oh, very good. Natalia, what are you going to say? Well, means it's not what? It's not constant or not linear. It's not like the temperature's changing, 1 degree every hour. It looks, it's at a, what do we write down? Over time. Jot this down. Over time. Temp, you can abbreviate that, changes gradually. Not constant. Gradually. It might change 1 hour, it might change 3 degrees, the next hour it might change 5 degrees, then it might change 1 degree. It's different, okay? Varied rates, no crack there, okay? Does it get warmer or colder throughout the day?
Warmer than colder.
You can't tell.
Well, I think you can tell because you know that
Like
no matter what the numbers are, they're still going to be positive. So it kind of gets warmer, warmer, warmer. It reaches its what would this call?
Vertex.
Peak.
The vertex peak. What's another good word? Well, just how about maximum? Guys, it reaches the maximum temperature of the day, and then it gets colder, not at a constant rate. Okay? And then it actually looks to me like it gets back to the same temperature at the end of the day that it was at the beginning of the day.
Probably.
Okay? So, but it changes gradually. It's no crock here. No constant rate of change. Okay. Jump to the next one. Have we done this one yet? Let's see what this graph does. Graph to the right shows the distance Tyrone is from his house throughout the day. Describe the change over time. So, that's how far he is from his house. Let's label these. A, the perfectly horizontal one will be B, C, D, and E. Okay? That's what I want you guys to do on the test Friday. Is and maybe we'll label them for you, or we'll remind you, is talk about each part. Okay? What's going on at his distance away from his house? What's going on in part A?
He's like leaving his house.
Okay, he's leaving his house, and do you think he's fast or slow getting away from his house? Yeah, I think part A, what do we write? He leaves home.
Vehicle.
He might be in a car, right? Leaves home at a fast, and is it steady?
Yeah.
Constant?
Yeah.
Right? At a fast, steady pace. Okay? What's happening in part B?
He stops for McDonald's.
Stops for McDonald's. For a long time or a short time?
Short
Goes
time.
to the drive-thru.
Short time. Very good. We're going to write stops briefly. Okay? Goes through the drive-through somewhere quickly. Get some food. Okay? What happens in part C?
Slowly walking.
He ditched his car.
Okay? Continues. He continues
but there's traffic.
away from home. From home at a slower pace. Slower pace than part A. Because the slope is not as steep. It's a less slope. What happens in part D?
He takes a nap.
Stops.
For how long?
For a long time.
Long periodically of time.
Why is he stopping for a long time? I mean, how do you know he's stopping for a long time?
It's a
He went
transient
shopping.
Stop.
Because
Or
guys, hey, this is time this
Long
way. In
periodically
part B,
time.
time only went, like a short amount of time. That's a long time.
Now he's shopping.
So he stops for
Groceries.
a long time. Okay? Again, there's no number, so we don't know how long. We don't care how long. But it is a lot longer than when he stopped on part B. The graph. And then, what happens in part E?
He goes home.
races home.
Does he stop on the way home?
No.
No,
How do you know?
because it's not flat.
Okay. Goes, we wrote this down, goes directly home at a steady pace. Okay? Alright. Alright, next, what we're going to have you guys do. With the person sitting next to you, and I'll try to hook you guys up if there's not enough people. But we have, I think there's 6. 1, 2, 3, 4, 5. No, 7. 7. All right, there's 7 graphs in here and 7 situations on different cards. Your job is to match up the situation with the graph. You and your partner. Okay?
Wait,
There's
we
7
didn't finish the
situations and
notes.
7 graphs. Thank you.
We didn't
Okay.
finish the notes.
We're going to go back to them. Hold on to those notes. But hey, everybody take 4 minutes.
So,
You two. And you and Ms. Burke. Okay. Turn around and work with Connor. Please. Oh, stop. You and Ange and Ms. D.
you want to hit pause on that
All
one?
right.
Ellie, pick up the card.
Hit pause. Thank you.
Ellie, pick up the card from the floor.
I couldn't get.
Welcome back.
I didn't find a yo-yo. All right. Alex uses a yo-yo. Sketch a qualitative graph. That means we're not going to use any numbers. Okay. To show the distance from the ground over time. Okay. So this one you got to do everything, guys. You got to make the graph and everything. Let's do this. So make a quadrant 1 graph. We're not going to deal with any negative numbers here.
Because it can't go underground.
Distance from the ground and time. Where do those labels go on our graph? Which one goes up the y-axis? Which one goes across the x-axis? Time goes on. Always put time, guys, on the x-axis, and then distance from the ground. From the ground. Okay. So when you start with a yo-yo, you guys all done a yo-yo before?
Yes.
Okay.
Yes.
Where is the yo-yo at 0 time compared to the ground? Is it on the ground?
No,
Do we
it's
start
on
at the
your
origin?
hand.
In your
Your
hand.
hand.
In your hands, would it be above the ground?
Yeah.
Okay, like look, here's a picture. It would be here, wouldn't it? When you started. So, it doesn't matter where you go, I'm going to go about right here. And then, as you start, I don't know, is the word called yo-yoing? Okay?
Yoing.
Yo-yoing. What's that yo-yo doing compared to the ground?
Falling.
It's getting closer, right? Does it ever hit the ground?
No.
Okay.
It's good if you're really bad.
Okay. So it's going to hit, it's going to go. It's not going to hit the ground, but then if you can do a yo-yo right, what happens to the yo-yo?
Goes up.
Goes up. When
Back
I
up.
was, I don't know.
And then does it get to the same spot that it started for the most part? Yeah. And then does that pattern continue if you do it right? What do you guys think?
That's a lot of
Well, wouldn't it
parabolas.
every time?
You'll see this is actually a trigonomic, it's either a sine or a cosine function graph that you guys will do in high school. That's it.
It's a cone.
Okay. Over time. You're holding the yo-yo in your hand, the distance decreases to the ground, it returns to your hand, you let it go again, it goes closer to the ground, it goes back and forth.
Mr. Pantini,
Okay? Yes, sir.
that's a lot of parabolas.
You know what? It's not a parabola.
But
Because it doesn't go. It's actually a sine or a cosine graph function, I think. Could be wrong. All right. Now let's do a tennis ball dropped on the floor.
Yay.
That's our tennis ball.
Nice tennis ball.
All right. Tennis ball's dropped on the floor. Again, do a quick graph. Doesn't have to be perfect. Rebounds to the height less than the previous ball. Sketch quadrant to represent the situation. Okay. What would our x and y axis be?
Axis time.
Definitely time, over time. So we're going to drop, and then,
Distance from ground.
yeah, distance from ground maybe? Or I wonder if it's supposed to be the height of the tennis ball from off the ground. That would be a different looking graph. But they'll be similar, just be kind of a reverse of each other. All right, so height less than its So it rebounds to a height. When you bounce a ball, guys, does each time it bounces, does the bounce get higher or shorter?
Shorter. It goes
Why?
half the distance.
Because
But it
it
doesn't have as
loses
much power as it-
gravity.
Yeah, gravity. It loses power, like acceleration. Okay. So let's say you drop it from about right here. It's gonna go down. Here's my question: does this one, when you drop it, does it hit the ground?
Yes.
Yes.
Yeah. So it's gonna go all the way down, even though over time, to a distance of 0. And then it's gonna bounce up, but it's not gonna bounce up as high as where you dropped it from. And then it's gonna bounce again. We're gonna do this. Okay. And it's gonna keep getting shorter and shorter until basically it stops. Okay.
And then that's like a straight line.
And then it would be a straight line where at?
The tops.
At the end.
Well, on the x-axis, because it's not going to be off the ground at all. All right, let's do it. Watch. You only got about 5 or 6 bounces in. Okay, then it stops.
If you try it outside, it
Okay.
maybe it'll
But time is going on. See, kids think that. Here's what kids think about this graph, and I get it. 'Cause I used to think this too. They think the ball is moving. The ball is not moving in this graph. It's the time is moving. Okay? So the time is moving while the ball is going up and down. Okay? Now, what if I did this? You don't have to draw this. What if I threw the ball on the ground?
It'd go higher.
It'd go higher.
Higher than what you threw it?
Yeah.
And it would
Okay.
move.
So that graph might look like something like this.
And it could move. Yeah.
Okay? We go, whoa. Okay, if you threw it.
We'd go,
Okay.
whoa.
Do it.
See, it went a lot higher than on the first one, but then it quit, guys, because gravity, and this is, tennis balls aren't that bouncy, you know. There's a Super Ball, you guys have seen a Super Ball, it would probably do something better.
I love it.
You know, so, different situations. All right,
Biggie.
the graph below displays the amount of money in Jared's account. Describe the change in the amount over time. So, we're talking about money in maybe like a savings account. You guys have a savings account?
Yeah.
Yeah.
Money in a savings account, okay, over time. And again, this is a discrete function because it's not continuous. All right, what's happening? I see only about three parts of this graph. What's happening in the first part?
He's gaining money.
More
Withdrawing.
specifically.
Depositing money.
More specifically. You're right. Money's getting into his account. Think about lines and linear stuff and slope.
Hey,
His money is increasing at a constant rate of change.
Yeah, guys, at part A, okay, we're depositing money, depositing cashola at a steady rate. Okay, depositing money at a steady rate. And then, what happens in part B when the line flattens out and becomes horizontal?
He doesn't put any money in.
Is time moving on though?
Yes.
Yeah, time's moving on, okay, but no money being deposited. Spelling issues today, people. Being deposited. Okay, no money being deposited. And then all of a sudden,
Buy a new car.
what happens from that point where it's flat at point B to where it's going to be flat at point, we're going to call that
He
C.
loses all his money.
He took money out, okay?
Well, just like
He
Sorry,
made
I-
what's the word when you take money out of your account?
Draw.
Okay? He withdraw, and look, guys, it takes you 1 second to withdraw money. It doesn't take a lot of time. You know, you just take $20 out, and all of a sudden it's gone, and it took you 1 second to do that. Okay? So he withdrew money, okay, and didn't put any more back in. Okay? And it looks like he withdrew all the money that he put in during part A.
And some more.
He withdrew the money that he put in part A. All right, let's see what else we got going on here. Okay. Anybody get a haircut recently?
No.
Totally.
Okay.
I cut my own hair.
Cut your own hair.
Yeah.
How many inches did you take off, Ange?
7.
7? Holy cow, you got some long hair. Okay. All right, the graph below shows the length of Kristen's hair throughout the year. Describe the change in length of her hair over time.
She goes bald.
Okay? Well, I don't think it ever went to 0.
No,
If it went all the way down to the x-axis, yes, or she would have gotten her head shaved.
Her hair looks
Okay.
like Lance's.
But it didn't go all the way down. So what's happening here?
She's growing her hair.
The hair's growing. In part A, the hair is growing, and then pretty sure that your hair grows at a constant rate. Okay?
Well,
Hair
wait.
grows.
What if you put chemicals in your head and it stops?
Ah, you can do that.
Or you could take vitamins.
We'll call it at a constant rate, or we'll just put that whole proc thing. So your hair grows at a constant rate. Now,
At.
what happens at this vertical line?
She gets
She cut her hair.
What happened? She went, what
this person here put
Yeah, you put at.
grows at a constant rate? At a croc. Guys, what happens in the vertical line?
She cuts her hair.
She got a haircut.
Maybe
Okay.
just tell all your hair out.
She got a haircut.
She got multiple hairs, but
Part B, she got a haircut. And here's my question. Is her hair shorter or longer than when it started?
Shorter.
How do you know?
Because it's lower than the starting point.
Yeah, 'cause it's right here compared to right here. So her hair is now shorter than what it was. Okay? So, qualitative graphs, people.